Okay, welcome to week 2 of the initiation of AC circuits, course 2A. Judging by the exam, most of you are on your way to getting a good grade. So congratulations. AC circuits, the one thing that I see from the exams though is maybe some of you need to get better acquainted with geometry. Okay, man, when I say geometry, I'm talking about sine curves. Okay, what is a sine curve? Mathematically, how do we how do we make measurements with it? And the importance of the sine wave is because electricity, AC electricity, is mainly um, done through a sine wave function. Understanding how the current and the voltage varies. They both vary in time, and AC circuits are time-sensitive circuits. So get to understand the timing involved with sine, mainly the sine curve. All right, and also vector quantities and angular quantities such as sine and tangent. Those are the two important ones. All right. So, and at some point we will bring in that there is basically two types of AC signals that we can have. We can have single phase, where everything runs with just one sine wave, or we can have a three-phase circuit, which is a lot of your big motors run on three-phase, and a lot of heavy-duty equipment as well, because three-phase is very efficient. That means you've got three sine waves. So you generate three sine waves. They're all separated by 120 degrees phase. And you ought to know by now what a phase is, okay? And what a difference is between sine 1 and sine 2, for example. Okay, but AC circuits then, the beauty of them is that they are time varying things. And so we add a few components that help you arrange your timing. First component that we talked about last week was the capacitor or capacitive devices. It's devices that use a capacitance. And capacitance is basically when we build up energy through an electric field. So we're talking about a current that is creating an electric field in a two-plate type of component. Okay, it could be just a simple capacitor. It could be a diode. It could be a number of other solid-state devices that have capacitance associated with them. But also two wires that are close to one another can develop the capacitance. So the capacitance then is related to voltage. But you don't get the voltage without the current. So the current comes first, then you produce the voltage. And that's why we say that the current leads voltage in a capacitive device. Current leads voltage in a capacitive device. And that makes a capacitive device sensitive to voltages. All right. In that if there is a jump in voltage, there's a sudden surge in voltage, well, the voltage isn't going to instantaneously change without having also simultaneously jump in current, because the current comes first before the voltage. Okay, so that's the capacitive device, is such a device that you need current to activate the voltage. Okay. The other important device that we talk about for the rest of the week is the inductive device. Inductive device is an inductor or a transformer, okay? And that works in the opposite manner that a capacitor does. In fact, whereas a capacitor is energized through a current that develops an electric field that creates a capacitance. The inductive device is generated by a voltage. The voltage then creates a current that is sustained in the inductive device. So basically, an inductive device likes to maintain a certain current level, and that's what it's used. That's how it's used as a filtering system. Okay, so one capacitor needs current to develop voltage, and that voltage is stored. So you've got energy stored in the form of an electric field, whereas an inductor is quite the opposite. You need a voltage to create an electric current. So the voltage comes before the current in an inductive device. Create the voltage, and then comes the current, and you get a steady current once you develop the proper voltage. All right. So the one device varies voltage, the other device varies current, and so basically they are opposites of one another. And when they work together, okay, there's a seesaw effect. Seesaw effect, what do I mean by that? Well, don't forget, capacitor stores energy in the form of an electric field. The inductive device stores energy in the form of a magnetic field. So what happens in the seesaw is that the one device takes its energy that's stored and feeds the other device. So say we charge up a capacitor, the capacitor gets charged up to a certain voltage, and then it feeds current through the inductor, it creates voltage through the inductor that creates current through the coil and charges that up. So you basically discharge the capacitor and charge up the inductor. And then you do that vice versa. The inductor that maintains a current now will exhaust that field by dissipating the current, feeding the capacitor, and it goes back and forth, okay, creating the seesaw effect. Capacitor, inductor, capacitor, that type of thing. And that is a phenomenon which we call resonance, and we'll discuss that in your next course, but not in this one, but just as a look ahead, that's what these two devices are used for in AC circuits. And basically, what do they do? Well, they filter. So when you want to tune in a channel or tune in a radio to a specific frequency, you use a capacitor with an inductor to tune in the proper resonant frequency. And then you tune in the proper radio station or TV station or whatnot. Okay? So that's what it's all about. But today we'll start looking into inductive devices. And inductive devices basically start, well, we know first of all that last week we talked about a current running through a wire in a coil around a ferromagnetic material creates a magnet. You have a north and a south pole. Now, but that's a DC, okay? What happens if that current is AC instead of DC? Well, what really happens is that because it's an AC, that current is going to be sinusoidal, which means it's going to be varying in amplitude, and it's going to be varying in direction. So when you have that situation occurring, you induce on a time scale magnetism into your core that can switch back and forth. Switch back and forth. Switching back and forth through a magnetic component, so it's a magnetic material, such as an iron core, okay, creates that magnetism within that iron core that fluctuates in magnetism. So if you put another coil at the other end of that, you create a coil that will pick up voltages from the induced magnetic field. All right, and that's what we call a transformer. All right, so basically we can transform. What does it transform? Well, it easily transforms voltage from one to voltage to the other. It can be a higher voltage, a step up voltage, or it could be a step down voltage where you start out with 120 volts and get something that's 24 volts. All right, step up, step down really apply to the voltage. Okay, and the voltage is the amount of voltage transferred is dependent on the number of turns that you do on the coil. All right. So basically, though, if you're stepping up voltage, you're going to step down the current because you have to maintain total power. And as power, as we know, is current times voltage. So if you increase one, you have to decrease the other, okay, and maintain the same power. So if you step up a voltage, you step down the current. And similarly, if you step up the current, you'll step down the voltage. Okay, so it's pretty interesting stuff, and we'll get through it this week, and it'll do just well. So let's get started.